Let's see. So you should be able to see the PowerPoint at this point and see me. All right. So are we ready to go?
Yes. Go ahead.
All right. So this is talking about work done with the Lunar Reconnaissance Orbiter, Lunar Exploration Neutron Detector. We're looking at, of course, hydrogen-bearing volatiles, by which I clearly mean water, or OH, at the Lunar Terminator in the Equatorial region. So let's see. Okay, it's not letting me advance that way.
Just use the arrows at the bottom of the, underneath your slide.
There it is. All right, so this is building on the work done, and you've already seen some of it this morning with epoxy and M-cubed, and also I forgot to include it on here, but the work with the Cassini VIMS instrument that saw hydrated minerals on the lunar surface, and in particular epoxy in 2009 showed an enhancement of the depth of the hydration signature at the Lunar Terminator, and there was some argument at the time as to whether that could be a phase angle effect or really an increase at the Terminator. So that's what we're exploring here to see how much hydrogen is actually isolated at the Terminators. We are sensitive with the neutron detection for a depth into the surface that's something else I need to update. Really, it's about 100 centimeters or so into the surface. So we probe about 1 meter deep into the surface. And unlike the other instruments that have been used that are seeing reflected light, we are sensitive day or night. We're looking at neutrons that are emitted from the lunar surface that are created by galactic cosmic rays impinging on the surface and releasing neutrons, so we can see everything on the night side as well as the day side. For this project, we'll be looking at just material within 30 degrees of the equator, so 30 degrees south to 30 degrees north, selected somewhat arbitrarily on the exact limits as all being within roughly the same range of phase angle in illumination from the sun, and basically the same conditions from the same diurnal period, etc. Okay, moving on. This is the LEND instrument, or rather, this is the sensor head for LEND that's on LRO right now in orbit around the moon since July of 2009. We've got a central collimator unit that has 4 detectors that we'll be talking about at the base of those barrels that you see the openings for at the top, and then 4 detectors around the sides, of which the 2 that we're particularly interested in that we'll be using, well, one of them is a thermal neutron detector that we're not using today, and another one is an uncollimated epithermal neutron detector. So looking at neutrons with an energy greater than thermal energies. And then down at the bottom of these 4 barrels are 4 more epithermal neutron detectors that have their field of view constrained by the width of the barrel, although there are also some fraction of neutrons from the moon that are able to penetrate through the walls of the collimator. And in fact, that's something we'll be depending on for this work. So here's a schematic of the instrument showing where these different detectors are. And the ones in particular that I just mentioned are the CETN, the uncollimated epithermal neutron detector, and CCETN, the collimated epithermal neutron detectors. The way we see things, if there is hydrogen in the regolith, it is such an efficient moderator of neutron energy that anywhere that there may be some hydrogen buried in the regolith, it will deplete the neutrons from the epithermal energy range and transfer them down into the thermal neutron energy range. So if we just look at the measured flux of epithermal neutrons, if there is hydrogen in the surface, we would see a local decrease in the flux that we're looking for, with a decrease in signal on the order of 4.5%, equaling about 0.1 weight% of water in the surface. Okay, so this is the kind of spectral information that was used to show with the epoxy data the presence of the hydration feature. This is an approximate model of reflectance for the surface integrated spectrum that you see from the example image that we have up above. Of course, the image doesn't have the spectral information. That would be from the May 2008 observations of Earth and the Moon by epoxy. And we were able to extract the spectrum of the Moon alone in reflectance from this sequence of data. And that's what I used to show that feature there. And then Jessica Sunshine used that to map out the location of observed hydration by the depth of that hydration feature, finding the greatest hydration, as I said, at the lunar terminator. So here's our kind of data. This is what we're working with. These are maps of the lunar flux over in latitude and longitude in cylindrical projection, with the green map up above being for our uncollimated epithermal neutron detector, and the blue map down below being for our collimated detector. Your eye clearly tells you that there are some significant differences in what you see in those maps, and that is consistent with the collimated detector sees a substantial component of neutrons that penetrate the walls of the collimator. They must start with greater initial energy when they reach the collimator itself, although it's diminished by the time it gets to the detector. So now that's of some concern for mapping things in high spatial resolution, but for this effort, it doesn't matter. And in fact, I even take advantage of it. It means that we can use the collimated detectors are really biased towards a higher energy range than the uncollimated detector. And so they're seeing somewhat different depths into the lunar regolith. We use the maps that you see here not only just to estimate the energy range that we're talking about and to illustrate that, but we use these essentially as a flat field for all of the data that we collect over about 3 years of the LRO mission. So each measurement that we take is a 1-second integration with LEND, and we divide it by the corresponding brightness that you see in this map in latitude and longitude, and then reorganize the data in local time versus latitude. I'm just going to skip past that. And so this would be a map of local time versus, well, rather of the neutron count rate in the collimated epithermal detector, so inside that collimator device, in local time in the long axis and in latitude in the short axis. So I binned it into 10-degree wide latitude bins, and it's been smoothed in the local time direction because signal to noise in here is always a challenge for the eye. So what we see is that there's a local minimum in the neutron count rate at approximately dawn, actually just a little bit onto the day side of dawn, and there's a local maximum in the neutron count rate in the mid-afternoon. So where we see a minimum in neutron count rate, that would correspond to a maximum in hydrogen in the surface, and where we see a maximum in the neutron count rate would correspond to a minimum in the hydrogen, or if it's in the form of water, it would be the driest region we can look at. In fact, we can invert this image to see it in directly proportional to the hydrogen concentration, with the greatest hydrogen concentration at approximately dawn and at low latitudes, and the minimum hydrogen concentration in the mid-afternoon. Now that's different from what was seen by with some of the reflected light instruments, where they saw something that concentrates more at noon. And of course, we can't fully explain that yet. That's going to take a lot of effort and thinking. But notionally, the biggest difference between us and reflected light instruments like LAMP and M-cubed and epoxy is that because we see to some finite depth into the surface, if we have hydrogen-bearing materials distributed over depth, then they also are going to have to take finite time to diffuse out of the surface, and then diffusing away from warmer regions in the lunar day side. So it may just be that diffusion effect, although that will clearly take some more investigation. Concentrating just on the region between 30 degrees south and 30 degrees north, indicated by this green band, we can construct just a plot of the distribution of the neutron count rate over local time. Now, I do want to mention that Shuai Li showed one of my older plots earlier during his talk briefly, and there have been some changes since that one. This is just showing neutron count rate, and I've inverted it so the minimum is at the top of the plot and the maximum is at the bottom of the plot, so that it's more proportional to the concentration of water. And
again, Tim, you have
yes.
about 90 seconds.
Okay, well, I'll be wrapping up quickly in a mad dash to the finish. Let's see, we also see this not just with our collimated detector, but we have similar information with our uncollimated epithermal detector. So here it is in units proportional to water, again limiting to the latitude range at low latitude. And here's what we see in looking at the neutron count rate in that plus or minus 30-degree range versus local time. We see approximately the same pattern of the maximum amount of hydrogen at the dawn terminator, the minimum in the afternoon, but in this detector we actually see an extended minimum that even stretches up to dusk and then comes back up overnight. And our model for what we're seeing, our mental model, is that however hydrogen-bearing materials are getting to the surface, and in a sense that we have no say right now on how they're being delivered, but anything that migrates towards the dusk side will be trapped into the surface over the lunar night, pass through the night until it reaches whatever is approaching the dawn terminator, migrating away from the warm regions of the moon. And then as it rotates into the day side, it will remobilize out of the regolith and move back towards the dawn terminator, so that you get a pileup of things at the dawn terminator, where by things, of course, I mean hydrogen-bearing molecules, OH, H2O, whatever else you can imagine. So let's see, we just wrap it up. That's basically the same as what I just said, but there are a few other things that I've been able to address quickly. The question has come up, is there something else other than hydrogen in the regolith that could account for that modulation? For instance, could there be some kind of instrumental effect? Well, if there were, because of the short orbital period of the spacecraft, any instrument artifact that caused a depressed neutron count rate at the dawn terminator, for instance, would have the same effect at the dusk terminator, and we don't see that kind of pattern. Could there be an orbital effect? Well, if there were, we would see a minimum on one side that would be conjugate to a maximum on the other side of the moon. And again, we really don't see that. We see a minimum, we see a maximum, but they are not conjugate to each other in local time. And in fact, we've also looked at the count rate that we measure over the whole moon and compare it to the altitude of the spacecraft at the time that we made the measurement. And there's really no correlation there. So we are not looking at some kind of pathological orbital effect or detector effect that is masquerading as a concentration of hydrogen at the dawn terminator. We're going to skip that kind of stuff, and I'll wrap it up there. All done.
Well, thank you, Tim, and we're going to do some questions for you, and after that we're going to open up, after a couple questions, open it up for discussion for the entire session. And before we do that, thank you to all the speakers this morning. It's really been a wonderful session, and good job. So George, go ahead.
Okay, question from Aaron. Does the slow accumulation of hydrogen overnight set quantitative limits on hydrogen derived from surface hopping?
That is something that would really have to be addressed by people who are actually working on the issue of surface hopping. It doesn't really, I mean, what we see is that there's some accumulation over the first couple hours of lunar local time after dusk. And so certainly that should be some kind of buildup there, but it's not building up over the entire lunar night. It's just over the first maybe 3 or 4 hours of local time in the lunar night. Presumably that would set quantitative limits on the ability of hydrogen to transfer over by hopping, But an additional effect that we have to deal with, and that is going to be a growing project, is looking at exactly how the vertical distribution of hydrogen in the regolith affects the fluxes that are that leak from the surface in different energy ranges. Dave Lawrence, who had been with the Lunar Prospector neutron spectrometer, our predecessor at the moon, had a paper about 2 years ago looking at this issue and showed that if you have a thin layer that is relatively hydrogen rich right near the lunar surface, it can paradoxically result in an actual increase in the epithermal neutron production. So we're going to be having to look at those issues because all of the calibrations that we have are based, for both Lunar Prospector and for us, were based on assumptions that you have a uniformly hydrated regolith down to essentially infinite depth. So we're seeing however far down our neutron flux comes from. And once we start manipulating the exact depth at which you may be isolating the hydration, that can have a huge effect, it seems, on exactly what we see. That was one question.
Indu asks, what is the contribution of the diurnal temperature variation in the surface and subsurface to this hydration?
Well, let's see. So again, this is something where there's potentially two issues at play. One is whether the temperature has an effect on our ability to detect the neutrons themselves, since temperature has an energy component, and the neutrons have to have some substantial energy in order to reach us. The energies that we're dealing with are really a factor of several to multiple orders of magnitude greater than thermal energies. So the temperature should not have a substantial effect on our ability to detect neutrons, but it at least needed to be considered. Then there's the issue of whether the temperature affects the actual distribution of the hydration itself. And that is something that I know is being considered by others. Schorghofer had a paper at LPSC last year looking at the vertical diffusion of water depending on, well, water molecules, of course, depending on the temperature of the surface and the subsurface, showing the ability of water molecules both to diffuse upwards as things warm up during the day and to diffuse downwards. But I think there's a lot of detail there that I'm not really able to address at this point, but we certainly have to keep it in mind.
Okay, we just got one other question from Raul. So what is the role of the changing detector temperature?
The temperature of the detectors themselves really should have no significant effect, but just because I say it shouldn't be significant, that's a different issue. In every orbit, since we're generally speaking going to be transitioning the spacecraft, through being illuminated and then being in shadow, we would get kind of a constant change. But every region on the moon has been seen with the detectors in daylight and the detectors in nighttime at some time. But of course, the local time effect, it's true. The local time effect, the detectors would, if it's a local nighttime, the detector would have to be in shadow to see that. It's an interesting problem. It should not have an effect. But that would be another one of those several things I need to investigate. But what it shouldn't do is it should not simulate what we've actually seen in the distribution of where we get maxima and where we get minima. Because, for instance, that dawn region where we see a local maximum in hydrogen and a local minimum in count rate, the spacecraft would always be illuminated when it's going over that region. And in the regions going into daytime, they really should be no different. But I guess I'll have to give it some thought.
Okay. And we just have a request that you repeat the LPSC reference that you mentioned.
All right, that was Norbert Schorghofer, and that was the LPSC in 2012. And of course, he had a talk yesterday, if I recall correctly. Yes, he did have one yesterday also. I don't recall the number for that, but you can look that up on the astrophysics data system, and you can get, of course, the spelling of his name from the schedule of speakers. So
I have a question that kind of brings this talk into context with some of the earlier talks. So if Amanda and Shui are still online, so did either the IR or the FUV observations with local time see an asymmetry between dawn and dusk of the hydration on the extreme surface?
So this is Amanda. I don't think that we do in the far UV. I mean, if so, it's pretty minimal. But I've always kind of, I mean, there's enough variation in the data, as I showed you, that is related to terrain type, that I think it's hard to say that there's variation between, or there's differences between dawn and dusk. It's something that, you know, I've been thinking about looking at a little bit more, but it'll be hard to pull out.
If I remember correctly, I think that Roger Clark and Jean-Philippe had looked at a region, it might have even been Ryder Crater, at near dawn and near dusk times, and there was a, they could actually view more water, and I mean actually water. So it was a 3 micron absorption in the daytime one that disappeared in the dusk, or close to dusk. So there's that variation.
Something I can contribute at least is I talked with Jessica Sunshine about some more of the epoxy stuff. It's just that the observations that were done with epoxy just didn't happen to see the dusk side. So it's not that they failed to detect it, it's that it failed to be in position to evaluate it.
Okay, that's good to know. Thanks. And so then, I mean, the other thing that I wonder is if this diurnal thing is going on and, you know, hydration is leaving at noon, where does that hydration go?
It all goes to the dawn. That would be my claim.
So you think it's coming off as water, or as what, and going to dawn?
Well, I don't know. I guess I would have thought that if it were free hydrogen atoms or even hydrogen molecules, the mass is so low that that would be quite speedy at a typical thermal energy and presumably would escape. So in order to be able to hop and not escape, and you should know this better than me, so maybe I can make a claim and then you can challenge it for me. That you really have to have something as massive as an H2O or an OH in order for it to hop across the surface without having a high probability of escape.
Yeah, I mean, that's right. If it's low, mass, it will most likely escape. So in order for the, you know, there to be some migration that's accumulating in cold areas and at dawn, it would have to, and it's released someplace else on the moon, it would have to come off as water probably. Because if it came off just as H2 or something, it would escape, and it wouldn't condense. I mean.
Now, if I gather one of the big problems though is that if we have H2O or OH that's in the free space above the surface, we have a high probability of photolysis by solar UV. But at that point, you have a relatively low-speed, low-energy hydrogen would be released and breaking that up, and similarly a low-speed, low-energy oxygen that would be falling back down to the surface ballistically, or at least 50% of the time, roughly hitting the surface again ballistically. What would they do when they reach the surface again? The oxygen presumably would just oxidize whatever it runs into. But could the hydrogens then form a new OH and wherever they're delivered and just continue their travel towards the Terminator?
Yeah, Tony Colaprid has brought up, or is wondering, what altitude would a hop of water or hydroxyl get? Would it be an altitude that LIVE could observe?
That's a question for Dana, I think.
Suspiciously silent.
Oh, I'm sorry. I had it on.
I'm the only one that got to hear that answer.
Okay. I had it on mute. Yeah. Okay. So, yeah, it would. Body would be able to see water hopping with the NMS. It would get to probably 50 to 100 kilometers. But I mean, and I know I have a histogram somewhere of the altitude distribution of water hopping, so I'll get that to you, Tony.
Actually, Dana, that's an interesting point. I hadn't really thought it would hop quite that high, but if we're getting to 50 to 100 kilometers above the surface, then that means that there could be water molecules distributed throughout the free space between the surface and LRO. And one of the things we've been considering is what effect that would have on neutron scattering. To have, if all, depending on what fraction of the relevant hydrogens around are in the free space above the surface, they may have an influence on the scattering and the energy distribution of the scattered neutrons.
But that would be time dependent, right?
Yes, that would be quite challenging.
Well, maybe it wouldn't be challenging. Maybe it would be helpful if you would expect that well, as Brian Butler is saying, hundreds of kilometers possibly.
Well, I don't mean challenging to the result. The result exists. The data are there. But it would be challenging as a calculational project to quantitatively interpret the results that we have.
Well,
So Tony, can the NMS detect water, or what? How does it do with water and OH?
Yeah, NMS should see water if, and they've been very careful to keep contamination as clean as possible, but it's always the tricky one, right? Because there's just so much water on Earth. So if it's very small amounts, they'd have to look for trends and whatnot, but no, it's certainly something they can see. And UVS can see OH and H2O plus if any of that water ionizes, but certainly if there's OH, the ultraviolet spectrometer should be able to see that too, if there's enough of it.
well,
It'd be nice to get some kind of prediction as to the column concentrations for water and OH if it's a diurnal effect, and that's something we can maybe look towards a prediction for LADI and see if they can at least constrain what's there. If they don't, put up the limits if they see nothing.
So are any of the lab people on still? And several of you have done studies of looking at bombardment of lunar type stuff with solar wind type protons and looking at the spectra. But do you have capabilities in your labs to do mass spectrometry of what comes off to try to understand better, what happens once you reach that saturation point, and to the excess ion flux that comes in, how does that come out? Raul says they can do it. Are you doing it, Raul? What's the answer? How's it come out?
I believe the Burke paper from a couple of years ago from Raul's group covered trying to look with the mesh spec while they were irradiating.
Okay, so Raul says that it shouldn't come out as OH, or if it is OH. But I guess what I'm thinking about is that if you have, I mean, these soils, the Apollo soils return kind of show some saturation. And if you look at the concentrations of hydrogen in the saturated return soils, you know, it takes some time to work up to that sort of concentration, but it is a nowhere near the exposure time on the surface. So, you know, you have this flux coming in that doesn't stick in there. So where does it go?
But Dana, don't forget that there's also, you know, been reported that 20% of it leaks out as neutral hydrogen. You know, so some of it may not have to form an H2 to leave or do the recombinant desorption. It might just now slip right out, sort of diffuse out as a neutral. And I wonder if those 20% numbers are really just, you know, well, of course, I mean, it's the implanted stuff that's leaking out. There's 20% right there.
Right. Yeah, that's a good point.
You know, and then how much H2? I mean, I don't think people really, I mean, I guess LAMP has looked at H2, but how much, you know, I guess you would know more about that, about the H2, the exosphere.
Yeah, we're just getting to that. Jason Cook is doing some analysis where he's sending, you know, all of the LAMP data and looking for the H2 fluorescence lines in that. And the Apollo 17 UVS set an upper limit, but I think we're going to be able to refine it with the LAMP data.
Yeah. But then out of that branching ratio, then how much of it turns into water? And I think it's the thing Georgia Tech folks are looking at is the H2 versus water in terms of that. How did Stella Kina call it? That inhibition boundary effect.
Yeah, I mean, I think you're right. Those branching ratios are important. How much goes to what?
Raul says he doesn't believe in the 20%, but I think that's. I think it's been confirmed by a couple of spacecraft. I will tell you, Dick Hodges thinks it's 99%, so I'm more comfortable with 20 than 99.
All right, so let's see. Any more questions and comments? I see some more typing going on. On saturation, you should get 100% out, but thermal.
So actually, the reason it's talking about
Let's see. So Brian Butler said to first order, the height is the vertical velocity squared. So Brian's talking about the scale height of the water. At 250K, the height is 5 kilometers or so, but there is a long tail, so you get some that go very high. All right, so So Raul, I mean, that's what I'm thinking too. Is I mean, when you get to the saturation point, you have to count for the entire flux. What happens to it all? And you know, I think we're getting close to the point where we can put all of the data together, the surface concentrations at dawn and dusk and the depth concentrations with dawn and dusk, and find out how much is migrating into the soil, how much is migrating through the exosphere. And with LADI, we can confirm the exosphere portion, hopefully. And once we get that, then we can also determine how much we expect to condense in the cold traps.
Tony Colapret says that LADI will dip to 25 kilometers and is often below 40 kilometers. The UV-Vis will nod and the UVF will nod and can see within a few kilometers of the surface before scattered light will become an issue. So really LADI would most only be seeing the tail. Well, I don't see any typing. Does anybody want to start furiously typing so that we don't end the discussion? Or, I don't know, my stomach